Welcome back to the Deep Dive. Today, we are pointing our telescopes way, way back in time. We're diving into a new discovery from the James Webb Space Telescope, the JWST. And honestly, it's one of those finds that's making scientists rethink, well, everything.
It's really shaking up our most basic ideas about how quickly the universe grew up.
Exactly. Our source material is all about this one galaxy that looks, for all intents and purposes, fully formed at a time when the universe was, just a baby.
A cosmic toddler at best.
So our mission today is to figure out how this is even possible. We're talking about looking back in time. What is it, about 12 billion years?
Roughly 12 billion years, yeah.
Yeah.
And that timeline is really the whole story here. You have to understand, the universe is about 13.8 billion years old.
Okay.
So when we look at this light, it's been traveling for 12 billion of those years to get to us.
But we're seeing this galaxy as it was when the cosmos was only 1.5 billion years old.
That's it, just 1/10 of its current age. This is an era we call the cosmic dawn.
And what were we expecting to see at the cosmic dawn?
Basically chaos. Little, messy, sputtering galaxies just starting to form. Not this.
And the team that found this, it was a pair of Indian researchers, Rashi Jain, a PhD candidate, and Professor Yogi Shweta. And they named it Alaknanda.
After a river in the Himalayas.
And the best part from the sources is that when she first showed him the image, his reaction was apparently just total disbelief.
Which is the correct reaction. I mean, you're looking at something that your models say shouldn't exist yet. The expectation for a galaxy that early was, well, that it would be irregular, clumpy, and a total mess.
Okay, so let's unpack that. The expectation was chaos, but the reality was a cosmic pinwheel. What does Alaknanda actually look like?
It looks mature. It's what the researchers call a fully formed spiral galaxy, a massive, beautifully structured cosmic pinwheel. It just looks like it's been around for billions and billions of years longer than it has.
And when you say spiral galaxy, we should be picturing something like our own Milky Way, right? Like the most organized, majestic structure you can get.
Precisely. And it's not just any spiral. They classify it as a grand design spiral galaxy.
What's the difference?
A grand design spiral has these two, very clear, very symmetrical arms that wrap around the core. It implies a kind of gravitational stability that should take an immense amount of time to develop.
And JWST got such a clear picture that they could see details in those arms, right? They saw something they called the beads on a string pattern.
Yes, and that's such a fantastic detail. Those beads are massive clusters of young, hot stars forming along the spiral arms.
Which is something we see in nearby galaxies today.
All the time. It's a sign of a stable, mature star formation process. Seeing that same organized pattern 12 billion years in the past. It's just wild.
So to really nail down how mature it is, let's talk stats. How big and how massive was this thing?
This is where it gets truly shocking. It's about 30,000 light years across, so roughly 1/3 the size of the modern Milky Way.
Okay, that's already huge for that era.
It is, but get this. It had already collected 10 billion solar masses worth of stars.
10 billion. In under 1.5 billion years. That's not just fast, that's a cosmic sprint. It's like building a city in a weekend.
And it wasn't slowing down. It was still forming new stars at a furious pace, about 20 to 30 times faster than our Milky Way is right now.
So it was big, organized, and super productive.
A complete system that just breaks all the cosmic speed limits we had in mind.
Which brings us right to the core paradox here. Why shouldn't a galaxy like Alaknanda exist so early? How did it happen?
Well, it really throws a wrench in the standard model of how we think big structures form. The idea was always that things grow hierarchically. Small things merge to make slightly bigger things over huge spans of time.
So we expected to find, like, little cosmic puddles of stars, and instead we found this fully formed, roaring river.
That's a great way to put it. For Alaknanda to exist, it had to assemble those 10 billion suns and form that stable disk with spiral arms in just a few 100 million years.
A few 100 million years. In cosmic terms, that's an eye blink.
It's unbelievably rapid. It really suggests the early universe wasn't this slow, clumsy builder. It was a very efficient, very fast architect.
So this discovery, it's adding to this growing pile of evidence from JWST that the early universe was just much more mature than we thought.
Exactly. Sophisticated structures were being built much, much earlier than our theories predicted was possible. It's forcing a major rethink.
Okay, so if it grew that fast, how did it get those beautiful, stable arms? Because creating spiral arms isn't easy, right? It requires some very specific, almost gentle conditions.
That's right. The long-standing theory is that you need what's called a dynamically cold disk to form stable spiral arms.
And what does dynamically cold mean for, a non-astrophysicist?
Think of it like a perfectly smooth spinning record. All the stars and gas are moving in nice, orderly circular orbits. There's not a lot of random chaotic motion. That calmness allows these large spiral patterns to form and last.
And the early universe was supposed to be the opposite of that.
Completely the opposite. We expected early galactic disks to be dynamically hot, messy, clumpy, turbulent, constantly being bombarded by infalling gas and other small galaxies.
So total chaos, not the place for a delicate spiral to form.
Not at all. So the big question for Alaknanda is, how did it overcome that chaos so quickly?
What are the running theories, the scenarios that could explain it?
Well, the first big question is how it got so massive so fast. Did it grow through violent mergers or more gently?
And the evidence points which way?
It seems to point towards a more gentle path. The scenario is often framed as smooth accretion versus violent mergers. If Alaknanda had gone through a bunch of big violent mergers...
You'd expect it to be a mess,
Yeah.
right? A big puffy ball of stars.
Exactly, a big central bulge. But Alaknanda is described as overwhelmingly disk-dominated. It's very flat.
And they can measure that, even from 12 billion light years away.
They can. They look at something called the bulge to total luminosity ratio, or BT. Basically, how bright is the central bulge compared to the whole galaxy? Alaknanda's is incredibly low.
So, not much of a bulge, which means it likely grew by smoothly pulling in gas from its surroundings, not by crashing into other galaxies.
That seems to be the most likely path for its mass, but that still doesn't explain the arms themselves.
Okay, so what's theory number 2?
Well, one idea is called clumpy dissolution. The theory is that those hot, clumpy early disks can eventually cool down and stabilize as the clumps dissolve. But that process was thought to take 1 billion years or more.
And Alaknanda is way ahead of schedule.
Billions of years ahead of schedule. So if that's what happened, it happened at lightning speed.
So what else could it be? Is there a third option? Maybe the arms aren't as stable as they look.
That's scenario number 3, companion interaction. The researchers spotted a smaller candidate satellite galaxy nearby.
Oh, interesting. So a little neighbor could be, pulling on it?
Precisely. The gravitational tug of war from this companion could have been just enough to trigger the formation of those two spiral arms.
So it's less of a stable internal structure and more of a temporary feature caused by a neighbor, like ripples in a pond.
It could be. And that's a really critical distinction. If the arms were induced by this companion, they might be short-lived. The underlying disk could still be dynamically hot and chaotic. The grand design could just be a fleeting illusion.
So that's the key, isn't it? Figuring out if this galaxy is a truly stable, mature system or just a temporary accident of gravity.
That is the million-dollar question, and it brings us to the next steps.
Right. To tell the difference between a real, long-lived spiral and a temporary, tidally induced one, what's the one piece of data they absolutely need?
They need to measure the kinematics of the disk. They have to figure out if it's actually dynamically hot or cold.
And how on earth do you measure the internal motion of a galaxy that far away?
With light. You use spectroscopy to look at the Doppler shift. You map out which parts of the galaxy are moving toward us, that light is blue shifted, and which parts are moving away, which is red shifted.
Ah, so you build a speed map of the whole galaxy.
You build a speed map, and if all the stars are moving in nice orderly orbits, the spread of velocities is low, it's dynamically cold. But if the speeds are all over the place, it's hot and chaotic.
And that would tell you whether the arms are a stable density wave or just a temporary tidal feature.
It would be the smoking gun.
Yeah.
And to get that data, they need to use an even more powerful tool, like the NISPEC instrument on JWST, or maybe the LMA observatory in Chile.
It's amazing what they can figure out from a few photons of light.
It really is. And it brings up that profound point about light travel time. I loved this quote from Professor Waddeducker. Someone asked him what Alaknanda looks like now.
Right, 12 billion years after the light we're seeing left it.
And he said, when people ask me about where it is at present, I tell them wait for 12 billion years to see where it is now.
Wow. That really puts it in perspective. That ancient snapshot is all we have.
It's all we have. Our theories have to fit what we see in that snapshot.
Okay, so let's summarize this deep dive. Alaknanda, this stunningly perfect spiral galaxy at the dawn of time, is forcing us to completely accelerate our timeline for how the universe builds things.
It tells us that massive organized galaxies could form incredibly quickly, either through some super efficient, gentle growth or maybe with a little help from their neighbors.
And that leaves us with a final, really provocative thought to chew on. The researchers themselves said that the keys to our present and future lie in the past.
Right. And if a galaxy one-third the size of our own Milky Way could be so mature just 1.5 billion years after the Big Bang, what does that say about how galaxies are supposed to form?
It suggests that maybe this rapid maturity isn't the weird exception. Maybe it's the rule.
And it raises this really fascinating question. Is our own Milky Way, which we think of as this modern, highly evolved galaxy,
Is it actually more typical of the early universe than we ever dared to imagine? Maybe the universe was just great at building perfect spirals right from the start, and we just couldn't see them until now.
and that is a mystery that's been 12 billion years in the making.
An incredible deep dive. Thanks for joining us. We'll see you next time.